So, this is going to be a slight review of what we saw in chapter 1, uh, mostly the ideas, and then a segue into chapter 2. So, what's the story so far? What do we know about cryptography? Um, till now, we can say that most of what we have know about cryptography is in heuristics, like how good an encryption system is and everything. We don't have a good way of measuring it. So how do we prove something is secure? We don't know how to do it yet. How to prove something is secure? Something is secure. Right? That is the very basic question that we have that we are trying to answer. And the question that we needed to ask to answer this first was what is secure, right? We need to define secure. We need to define secure. And that was a big issue uh, for the very reason that cryptography for a very long time was considered an art. And it's art in itself inherently is hard to analyze. Like some people like Renaissance era painting, some like modern art. I do not at all understand modern art, but I am not an expert in this field. I cannot say this. I have no idea what's good in some painting compared to another painting, but they're both valuable, and that makes it hard to analyze for someone who has no knowledge. Even in art, it's very subjective. However, if we want a definition of something to be secure, if we want some security, we cannot have something to be subjective. I can't say, this is super secure, and then have it break because it was secure according to my definition of secure. No, we need something that should be more or less um, objective in its quantifying, in its qualities. Everyone who sees it should be able to say, yes, this is secure or this is not secure. And so cryptography started to develop into a science. Cryptography started developing into a science in about 70s and 80s, uh, and developed into what is now called the modern cryptography. Um, became a science, became a science in 70s and 80s, which is, if you think about it, extremely recent, right? That's probably the time your parents were born or something. People before that did not consider cryptography as a science. Yeah, it's pretty recent. And so when it becomes a science, you need formal definitions, you need criteria, all these things. And so some core principles are established. Core principles, which I listed down in detail last time, but I'm going to give a brief synopsis of the principles and their underlying importance. The first thing we needed was formal definitions of everything. Formal definitions. Definitions. And formal definitions are really important. We need them to be precise mathematical models and definitions of what security means. Mathematical models and definition of what security means. So we are not just trying to make the formal definition of what secure is, but also of a security system, of your encryption, of your decryption, all the algorithm. All of this needs to be written down precisely so that we can study that. And why is that? So, along that, along with that, we need our assumptions. What are the assumptions we are making? How should they be? Well, first of all, they should be clearly stated. They should be unambiguous, and they should be as minimal as possible. Minimal. Okay, you don't want to rely on assumptions that might not be true. You want things to not break down, even if one of your assumption isn't complete true in complete generality. You should be able to show, oh, even if that statement is false in all generality, hopefully it is true in this very specific cases. And the third one we had was proof of security. Proofs of security. Because the only way you can get someone to use your encryption system is if they can believe that your system is secure. This also moves away from design, break, patch. So you don't want to design a system and be like, haha, yes, this is completely, this is a very secure system. Someone finds a flaw, you patch it, you again say, oh, it's very secure, second flaw. You should be able to demonstrate that, no, this is secure, this has no flaws, so that you don't need to work on the system again and again. Yes, there might be some design flaws that could come up in its application, but the inherent algorithm should be secure. Okay, and why are these definitions and all these properties so important? So, importance of definitions, their usage, design, analysis, and usage. Analysis and usage. Okay, so first of all, formal definitions are essential for the design, analysis, and usage of cryptography. Okay, you are forcing a designer to think about what they really want to do and what is essential for this design. Okay, forces designers to think what they are trying to achieve, think what they really want, and what is essential. Okay, is essential. Because eventually, how are you going to understand? Let me just write this in quotes. If you don't know if you don't understand what you want to achieve, how do you know that you have achieved it or not? If you don't understand what you are trying to achieve, how can you know? How can you possibly know if you have achieved it? Okay, and for that sake, it is really important to know what you're trying to do. What is the meaning of what is the goal you're trying to work towards? You need to have it set. You need to have it as more or less objective as possible. Okay, and it also enables meaningful analysis meaningful analysis, valuation, evaluate, V-A-L-U-A, V-A-L-U-A-T, evaluation of and comparison of schemes and that allows us to actually use these schemes. So usage, for example, allows us to understand the security guarantee to use. Allows us to understand the security guarantee. To use the scheme as a part of a larger system and allows the substitution of one scheme for another if they both satisfy the same definition. And allows substitution for another satisfying the same definition. Okay, so these are really important things because even if one system you say, oh, I have the scheme, you should be able to present to someone, explain to someone that this is secure so that they can possibly use it in a bigger system. Maybe you're using it to secure some one very particular thing, but now this thing could be used in the security of an entire bank, for example. Just you're securing one credit card, but that same thing could then be used to secure an entire bank. I don't know. And suppose one such scheme is then proved to be not safe enough. But if the definitions of that scheme was originally trying to satisfy, if you can show that the new scheme that you have satisfies those definitions actually, then you can just put these put this new scheme instead of the old scheme. So replacing becomes easier if you know exactly what conditions you are trying to satisfy and what are being satisfied. Okay. So that brings us to trying to define what is secure. Okay. So what is secure encryption? Question mark. Okay. So let us try to work towards the informal definition that we had last time. Well, let's make a first idea. What does it mean for encryption to be secure? Impossible for the attacker to obtain the key, for attacker to learn the key, Okay. Well, this has a lot of problems. It is necessary that the attacker should not learn the key. Necessary, necessary, but definitely not sufficient. Not sufficient. Because The key is just a means to an end. Like the important thing is the ciphertext. Sorry, is the plain text, right? If your key is not revealed, but your plain text somehow is revealed, that is absolutely useless, right? So definitely, the key being secret is not enough. If your plain text is revealed, that is worse than the key being revealed, right? Now, there are other things also. If, for example, instead of private key, we were doing public key, the public knows the key. There are still systems where even if the key is known, the security is secure. So, key leaked, but still secure systems exist. But still secure systems exist. Okay, so such systems exist, and we should be able to define what security means even for them. Okay, so it is not important if the key is known or not. What about the ciphertext? So impossible for the attacker, impossible for the attacker to learn plain text from ciphertext. Okay. Well, what if we say that the attacker should not learn the plain text from the ciphertext? Sure, but what if they say learn 90% of the ciphertext? So what about 90% of the plain text? Plain text. If they learn 90% of the same of the plain text, can you really call that secure? Yeah, you're probably not going to be saying that's secure, right? So let's go one step further. Impossible to learn any character of the of the ciphertext. Impossible to learn any character of the plain text. Well, this seems like it's really strange, and you should not learn any character of the plain text, right? But not all information is just in the characters, right? What if some other information of the plain text is revealed? What if some other information of plain text is revealed? Plain text is revealed. For example, if the number of troops attacking is more than 10,000 or less than 10,000, for example, if the number of troops is more than or less than 10,000, right? So that becomes an issue. Sure, your number is going to be a 5-digit number. Well, it's more than 10,000. If it's a 4-digit number, it's less than 10,000. How do we keep this secure? If the code is attack or retreat, then attack is ATTACK, 6 digits. Retreat is RETREAT, 7 digits. You can tell from the ciphertext that the code is, if you know whether it's attack or retreat, even though you don't know which of the ciphertext it is, plain text it is, you can't decrypt it. You know it's going to be retreat if it's 7 and attack if it's 6, right? Another thing is, what if it's guessed? What if it is guessed? Is it secure? Is it secure? Suppose my algorithm is going to guess what the code is. Is it still secure? Can I talk about, oh, how many guesses I make, and if I get it in one of the three ways? Okay, I don't know which one of the three things it possibly is. I'm going to guess it is exactly this one. I should be correct 1/3 of the time. Suppose I'm right 2/3 of the time. Is that good or bad? Is that still secure if I can guess it 2/3 of the time rather than only 1/3 of the time? Well, all of these things mean we need a more stringent definition. So we get a correct definition, correct definition, which is still, informal, regardless of whatever information of any prior information the attacker has, information the attacker has about the plain text, about the plain text, no new information must be leaked by the ciphertext. No new information must be leaked, must be leaked by the ciphertext. Ciphertext. Okay, so first of all, this says whatever information they previously had. If they knew it was a 6-digit, if the message is 6 digits or 7 digits, whatever, they should not be, after the message, be able to say, aha, now I have this extra information. Okay, the number of troops is more than 10,000. Okay, the message is going to be a 7-digit number, a 7-digit message. There should be nothing they should be able to gain that they didn't know previously. Okay, how to form. Now the question is how to formalize this. How to formalize. Question. Oops. Question. How to formalize. Formalize. Okay, and to do that, we need some amount of probability theory. Probability theory. Okay, so in case you haven't done enough probability before, here's going to be a brief review of the things we are going to be using. Brief review of probability. Brief review or EVIEWR EV review of probability. Okay, so first, a random variable. Random variable is defined to be a variable that takes on discrete values with certain probabilities. Certain probabilities. Okay, so generally x, where x can be 7 in 0.3 of the times, can be y 0.2 of the times, and whatever, some other thing. Okay, so you have a random variable. The probability distribution of a random variable, probability distribution, of a random variable specifies the probabilities with which the values specifies the probabilities probabilities with which the variables takes on the values with which the variable takes on each possible value. Takes on each possible value. Okay. Note, each probability must be between 0 and 1. Each probability must be between 0 and 1. And second, the sum of all probabilities should always be 1. The sum of all probabilities should be 1. Okay. Third definition, event. An event is is the outcome of a particular experiment, or an occurrence in a particular experiment. So a particular occurrence in some experiment. Okay. Generally, we denote the probability of an event by prob E. So PRB or just PRE is going to be the probability of event E. Probability of an event. Okay. Conditional probability. Conditional probability. What does conditional probability means? The conditional probability is the probability that one event occurs knowing that another event has occurred. So, for example, the probability that your first card is the ace of hearts is 1 out of 54. Like if you're playing with a normal deck of cards, the probability that your first card is ace of hearts is 1 out of 54. Suppose your first card is king of hearts, then the probability that the second card of is ace of hearts is now no longer 1 out of 54, it is 1 over 53, right? If your first card was ace of hearts, then the probability that the second card is ace of hearts is actually 0. You can't have the same card twice in a deck. So conditional probability, the probability that one event occurs, given that another event has occurred, some other event has occurred, given that some other event has occurred. Okay, and this is written probability of A knowing probability of A given B. So is equal to, well, probability of, so we are just using PR, probability of A and B divided by probability, so PR of B. So probability of A given B is basically what is happening. Well, what is the probability of both event A and B happening? Well, take that, and now you in fact know that event B has already occurred. So divided by probability of B. Okay. Two random variables are independent. Two random variables are oops, wrong place, are independent if for all x and y, for all events or occurrences x and y, for all x and y, the probability that x is equal to x, small x, given that y is equal to y, is equal to probability that x is equal to x. Okay, in that case we will say capital X and capital Y are independent. Okay, so whatever the outcome of y, it does not affect the outcome of x. In that case, x and y are independent. Okay, these are my initial definitions. Now let's get to some important results / theorems. First is the law of probabilities, law of total probability, total probabilities, say E1 to En, E1 to En are a partition of all possibilities, are a partition of all possibilities, partition of all possibilities. Then for any extra, then for any A, any event A which could happen, the following should be true. The probability of the event A happening should be equal to the sum of all probabilities of event EI and A happening. Okay, because EI are all the possibilities that could potentially occur. Okay, and this is equal to, by the result on conditional probabilities, equal to the sum probability of the event A happening, knowing that the possibility EI has occurred, divided by the probability of the event EI. Okay? Some other notations that we are going to be using, so this is the brief review of probability that we have from before. Okay, now we shall start using this in our cryptography. How are we planning to use this with cryptography? Okay, notation, just a brief review. We will denote by K the key space which is the set of all possible keys. Set of all possible keys. And C will denote the ciphertext space. Ciphertext space, which is the set of all possible ciphertexts. Set of all possible ciphertexts. Okay, great. We now use probability distributions. So let M be the random variable denoting the value of the message. Let M be the random variable denoting the value of the message. Okay. So in that case, where does M come from? M comes from the message space M. So M ranges over my message space M, my fancy written M, and this reflects RF reflects the likelihood of different reflects the likelihood of different messages like KELH of different messages being sent by the parties. Being sent by the parties, given the attacker's prior knowledge. Given the attacker's prior knowledge. Okay, so we assume that the attacker knows the probabilities of these messages being sent. Okay, so for example, we are going to say probability that the message is equal to attack today is equal to 0.7. And let us say the probability that the messages don't attack is 0.3. Okay. We will let K denote the key. Let K denote the key, and denote the random variable. K be a random variable denoting the key. Let K be a random variable denoting the key. Okay. Well, then the K ranges over my script K. Then K ranges over K, right? Over my fancy K. And we have some let us fix some encryption scheme. So let me just bullet these points. Okay. We are encrypting the message by some encryption scheme, which we are going to fix. Fix some encryption scheme, ENCRY, encryption scheme, gen encryption decryption. Okay. And here, gen actually gives us the probability distribution for k. Defines the probability distribution. T distribution for k. Oops. So what does that mean? My probability distribution is the my generator gives me some probability of how often is one key getting selected. So if we are, for example, dealing with the shift cipher, right, which is just moving everything by one constant letter, then I have 26 possible values that I can move everything by. Probability of that generally is going to be, probability that I'm shifting everything by 7 is going to be 1 over 26, right? So probability of k is equal to k is equal to probability, oops, is equal to probability that the generator outputs key k. Okay. Now note the random variables for the message and the key are independent. Random variables for m and k are independent. Okay. What does that mean? Well, the message party does not send a message that depends on what key I should use for the encryption. The message that a party sends, that a party sends does not depend on the key used to encrypt the message. Depend on the key used to encrypt that message. Okay, so there are no really weird rules going on, like if the length of my message is even, then I will shift by n. If it is odd, then I will randomly choose 1 to p, 1 to e, a to e, and shift by it. No such random rules. It is perfectly independent. M and k have no relation to each other than the encryption scheme. Okay. So, how does, given all this notation and definitions, how does my experiment work? How does my encryption work? Well, first, we need to define some distribution on the message space, right? Oftentimes, to define probabilities on the here, right? Using the different likelihood of the message space, we have some of that. So fix encryption scheme, fix encryption scheme. Uh, generator, encryption, decryption, and some probability distribution, some distributions on M, on my messages, and then do the following randomized experiment. Consider the following experiment. Following randomized experiment, which is first, well, this is the standard way we encrypt. Choose a message. According to the given distribution. According to the distribution. Okay, so if a message has probability 0, you should not be taking it. Choose a key. Sorry, you can't choose a key. You have to generate a key. Generate a key. Okay, using the generating function, which is gen. And the third, compute C, which is equal to, oops, this now looks like an O. Compute C, which by definition, you know what? C, which by definition is equal to encryption using the key K of my message M. Okay. Well, this now defines a distribution on the ciphertext. This defines a distribution on the ciphertext. Why is this a distribution on the ciphertext? Because not every ciphertext might be equally likely. Some ciphertexts might not ever occur, right? Given some messages M, you would never be able to get some ciphertext. Right, some ciphertexts might be more likely depending on if the probability of a certain message is, let's say, 0.99, and you have two keys, maybe one with probability 0.7, the other with probability 0.3. Then the encryption of message 1 with key 1 is much more likely than encryption of message, let's say, 2 with key 2, right? So let C be a random variable, denoting the value of the ciphertext in this experiment. Denoting the value of the ciphertext in this experiment. Okay, so let us do some examples. Let's do the easiest one, the shift cipher. Consider the shift cipher. Consider the shift cipher. In that case, all my keys are 0 to A to Z. So K is equal to A to Z, which in this case, probability of key is being any letter K is going to be 1 over 26. There are 26 possible letters. So let me just actually say this. This is going to be confusing. So 0 to 25. Rather than 1 to 26, let me say it's 0 to 25. let us suppose my message spaces are, say my message space M is okay. Say the message is with probability M, the message is A, and with probability 0.7, and the message is B with probability 0.3. Okay, then what is the probability? Actually, let me just do this. Let's go with Z. Whatever. Not that it makes a difference, but let me just copy the example. So the question is, what is probability? What is probability of the ciphertext being equal to B? Question mark. Well, let us calculate how we get the ciphertext to be. There are two possibilities. One, either the message is M is equal to A and K is equal to 1, or 2, M is equal to Z and K is equal to 2, right? In either of these cases, I'm going to get my ciphertext is equal to C, and these are the only two possibilities. If I use any other key K with message A, I am not going to get B. Similarly, if I use any other key K with message Z, I'm not going to get B. Right? So the total probability of C being of the ciphertext is equal to B is equal to the probability that the message M is equal to A multiplied by probability that the key is 1, K is equal to 1, plus probability that M is equal to Z multiplied by probability that K is equal to 2. Okay. What are the probabilities? Probability of message being A is 0.7 multiplied by key being 1 is 1 over 26 plus probability of message being Z is 0.3 multiplied by 1 over 26. So the total probability is 0.7 times 1 over 26 plus 0.3 times 1 over 26. You can pull the 0.7 and 0.3, 1 over 26 common, and you get 1 over 26. Okay, so that's our first example. Let's look at another example, example 2. Except this time, rather than single letter, let's consider the larger ones. Consider M is equal to 1 with probability 1/2, and probability that message is actually 10 with probability 1/2. Well, in that case, what is the probability that the ciphertext C is equal to RQH? Okay, in this case, this is going to be the probability that the ciphertext is RQH given that message was 1, M is equal to 1, multiplied by the probability of message is equal to 1, plus probability that the ciphertext is RQH message is equal to 10, and sorry, this should have been PR, not M. Probability that M is equal to 10. Well, in the first case, can it happen that the message is 1 and my ciphertext is RQH? P. And the answer is yes if my key is 2, right? If my P is Q, then if my key is 3, my bad, not 2, then I have O goes to OPQR, N goes to OPQ, and E goes to FGH, right? So in case that the key is 3, I get that my message is exactly RQH. That means the probability is 1 over 26 that the message is 1 and the key and the ciphertext is RQH, multiplied by what is the probability that the message was 1? Just 1 over 1 over 2. Plus, well, what is the probability that the message is the ciphertext is RQH given that the message was TEN? And if you go through all the keys, none of the keys is going to give this as the ciphertext. So the probability of this is 0 times the probability that that was the message, and in this case, the total probability is actually 1 over 52, and that is my conditional probability. Okay. So my informal definition of secrecy that we had before can now we can start trying to formalize it. Okay. So perfect secrecy, 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 which was to say, oh, regardless of any prior information, the ciphertext should not lead any additional information. Let me just write it down again. Informal, regardless of any prior information, the attacker has about the plain text. The attacker has about the plain text. The ciphertext should not leak any additional information. The ciphertext should leak no additional information. No information about the plain text. About the plain text. I mean, it can leak additional information like I am using a hexadecimal code or something by how it is written, but it should not leak any additional information about the plain text. It was my informal definition of perfect secrecy. So now trying to formalize it. Trying to formalize it. Formalize. Okay. So we are now trying to formalize it. What information can the attacker know about the plain text? Well, the information that the attacker can know about the plain text is the distribution of M. So we are going to say attackers information about the plain text about the plain text is equal to the attacker known distribution of M, attacker known distribution of M. And then what does it mean? The perfect secrecy means that observing the ciphertext should not change the attacker's knowledge about the distribution of M. Perfect secrecy in this case means secrecy means that observing the ciphertext should not change the attacker's knowledge knowledge about the distribution of M. It definitely shouldn't change to 100% this one message and 0% these other messages. But even otherwise, it shouldn't change it to say, oh, 90% of the 90% is going to be this message. That's still bad, right? And so that allows us to write the formal definition of perfect secrecy. Perfect secrecy formalized. So formal. An encryption scheme and encryption scheme, which is basically the combination generation, encryption and decryption with a message space with message space M and key space and ciphertext space C is perfectly secret. If for every distribution over M, if for every distribution over M, every M in M, and every C in C with probability C of C is greater than 0, it holds that the probability that the message is M with the knowledge that the ciphertext is C should be equal to the probability that the message was M. What that means in basically is that i.e. the distribution of M does not change upon conditioned on observing the ciphertext. Does not change conditioned on observing the ciphertext. observing the ciphertext. Okay, and that makes sense as my definition, right? Given a message, I send it to someone. The other person should not be able to tell if the original message was M or M1 or M2, but they shouldn't even be able to guess, oh, it is 90% this one. It should not change their ability to guess or what they think of the probabilities are. Okay? So nothing should change. They should stay equally confused in a way, right? Example, consider the shift cipher. Consider the shift cipher as an example too. Um, consider example 2. So let me just say, consider the case of example 2. Consider the case of example 2. Okay? Take M is equal to 10, C is equal to RQH. Okay? Then the probability that M is equal to 10 and C is equal to RQH, well, we saw that this is equal to 0. And this is definitely not equal to the probability that message is equal to 10, right? Which was 1/2. And so this is not secure. Therefore, shift cipher is not secure. Okay? Let's do an important theorem that will be useful. Bayes theorem. Bayes theorem. Oops. Bayes' theorem. What does Bayes' theorem say? Well, in easy terms, it says probability of A conditioned to B is equal to probability that B conditioned to A multiplied by probability of A divided by probability of B. Okay? Well, why is this true? Proof. I'm not going to write the complete proof. I'm going to leave one step to you. Let me just say probability of A condition B multiplied by probability of B is equal to probability of A and B, which is equal to probability of B conditioned A multiplied by probability of A. Right? If you scroll up, when we defined probabilities, right, we said that the probability of A conditioned B is equal to probability of A and B divided by probability of B. Moving probability of B to the other side, I get probability of A condition B is equal to probability of A time probability of B is probability of A and B occurring at the same time. Okay, so this is a really easy theorem, but it is quite powerful. Okay, for example, example. So example 4. Consider the shift cipher again. Shift cipher. Let the probability of m is equal to high is equal to 0.3. Probability that the message m is no is equal to 0.2. And the probability that the message is in is actually 0.5. Well, then in that case, what is the probability that message m is equal to high under the condition that the ciphertext you saw was xy? Well, that is the same as probability of the ciphertext is equal to xy and the message is high times probability that the message is equal to high divided by probability that the ciphertext is equal to xy. Okay? Well, to solve this, let us solve the individual probabilities. What is the probability that the message is xy and the probability the ciphertext is xy and message is high? Well, probability that c is equal to xy and m is equal to high is equal to 1 over 26 because there is exactly one ciphertext which gives this. Probability that ciphertext is equal to xy is now slightly harder to compute. This needs 3 conditional probabilities. Probability that c is equal to xy under the condition that the message was actually high. I know this is funny because we are trying to compute this. The message started. Is that what you're trying to do? No, okay. Okay, no. Okay, fine. This is fine. 0.3 plus probability that c is equal to xy, given that my message space was message was actually no, into 0.2 plus probability that c is equal to xy, given that the message was actually in times 0.5. Well, this is, in the first case, this is 1 over 26. There is exactly one key, point times 0.3. Plus, in the second case, there is also one key, which works, into 0.2. In the third case, there is no key which works. So, into 0.5, not 0.05, 0.5. And so the total probability is 1 over 52. Right? And so, what is the probability that the message is high given that the ciphertext that you have received is xy? Well, this is probability that the ciphertext is xy and the message was high multiplied by probability that the message was high and divided by the probability that the ciphertext was xy. which after computation is 1 over 26 into 0.6 into 0.3 divided by 1 over 52, which is equal to 0.6, which is not equal to the probability that the message was actually high. Right? So in conclusion, again, we get that shift cipher is not perfectly secret. Therefore, shift cipher is not secret, not perfectly secret, perfectly secret, perfectly secret. At least for 2 or 3 character messages. Character messages. Okay. So next time we'll see how to construct a perfectly secret scheme. Can we construct a perfectly secret scheme, and how to construct one such? Okay, let me stop this one.